So hello, welcome to the second day of chapter 28. I want to say chapter 28. We've been talking about single slit and double slit and even diffraction from a thin film, but in the general, diffraction and interference. And the last thing we talked about was a single slit and how if you shine laser light through a single slit, you'll get a diffraction pattern. Oh, before I get into it, quick announcement. Don't forget there is no homework due tonight because I'm just finishing the chapter, today. So no homework tonight. Tonight being the 11th. If we can get a diffraction pattern from a single slit, there's no lot, and we can get a diffraction pattern from two slits. Logically, we should get a diffraction pattern if we add even more slits. And you could actually get a diffraction pattern for any number of slits. And this led to the creation of what is called a diffraction grating. We talked about diffraction gratings once before in this class. That diffraction grating I used to take white light and separate into its components to create a rainbow of all the individual colors. And all the diffraction grating is trying this interference pattern. A diffraction grating is an equally spaced parallel slits. Traditionally, it's several thousand lines per centimeter. It's actually not really slits as much as lines on a piece of glass. It's just, if you have a dark spot and light can go on either side, it's kind of the same as having two slits when they're so thin. As I said, thousands of lines per centimeter. Now, the intensity of the pattern on the screen is the result of interference and diffraction. But basically, if we just had the one slit, we'd have an interference pattern. If we start adding infinite numbers of slits, we're going to start having a crazy complicated interference pattern. Now, for doing this, we're going to define D as the space between slits. How far from here to here? And defining D as the space, for the record though, diffraction patterns aren't normally phrased that way. They're normally given as lines per centimeter. If I take a look at the one I have here that we saw in class before, you can see it's 1,000 lines per millimeter. I said lines per centimeter. Lines per millimeter work too. That's just the inverse of D. Because D is how many centimeters per line, or how many millimeters per line in this case. So if something is 1,000 lines per millimeter, as this one is, that means the value of D is 1 divided by that number, because it's just the inverse. How many millimeters between line, or how many meters between line. So there's the value of D for this one. But what will happen is you will have maxima show up, just like your single or double slits. And the equation for maxima actually is going to follow basically the same format as our single slit, where we'll say that D sine theta goes as m lambda, where m is any integer. Now, what this says is the angle at which you have the maxima will be different with different wavelengths. And here's the cool thing about diffraction patterns. If you just take white light and shine it on a single slit or a double slit, you're not really going to see the pattern. You're not going to see the pattern because those diffraction will happen, but it won't get interact. With a diffraction grating, so much diffraction happens, so much interference, that a diffraction grating will have different wavelengths operate differently. And that's why this separates the wavelengths. It's where you see, and I was trying to make it so that I could have like the colors show up well and you could really see it. But I find like in real world, I can see the colors, but in here, you can kind of see there's a little bit of reddish to green here. But, oh, there you go. I got kind of a pattern going, red to purple, and with the light reflecting off of it. And the reason you get things to separate out to the components, the reason you can take a white light and turn it into a rainbow, is because we're dispersing all the colors, and they're all interfering in different ways. And maybe someplace red will be constructive and violet is destructive, so it will look red, or vice versa, and it will look violet. And that's the general idea, that diffraction grating is just an infinite number of slits. Or not infinite, but a shit ton of slits, and that we can use to look at interference patterns. Okay. So, example problem. Helium neon laser has a wavelength of 632.8 nanometers. That's the wave. That's just a regular red light, like a red laser pointer. It's a helium neon. That's the color of all basically red lasers. Helium neon makes a laser really easily. and it's used to calibrate a diffraction grating. If the first order maxima occurs at 20.5 degrees, what's the spacing between adjacent grooves? First order just means m equals 1. And this is my equation for diffraction grating. So if I want the spacing between grooves, that's d. I'll just divide both sides by the sine of theta. And I can just plug in my values and say, that's the answer. Now I kind of just kept it in nanometers. I didn't bother converting my 632.8 per meters. I probably should have. But either way, you end up with 1.81 micrometers. But that's the general idea. Kind of the same as a single slit or a double slit. It's just a lot of slits. Any questions though? Now, all this diffraction and interference is because light is a wave, right? And once again, we've already covered that light's also a particle. That's going to be in a lot more detail. I want to say it's next chapter, but it might be the chapter after that. There is one other important thing because light's a wave. So let's say light, as we know, is an electric field and magnetic field oscillating, where the electric field and magnetic field are perpendicular. So let's say, there we go. Let's say, for example, that my E field and B field, my electric field and magnetic field, is coming, I have light shining at you. Let's pretend that. And that I'm going to say, what if my wave looks like this as it comes towards you? And what I mean when I make these arrows is that this, I want to say red is electric field, that my electric field is bouncing like this. And my magnetic field is bouncing like that. Right? When I say the arrow, that arrow is just saying it's going from here to here and bouncing between them. And so my electric and magnetic field is just doing this. Well, if I just shine light at you, some of it might be bouncing exactly like that, but some might be like this, or like this, or like this, or like this. The direction of the electric field, whether the electric field is up and down, or if the electric field is left and right, or if it's at some angle in between, that's kind of arbitrary most of the time. And most light sources put off light where the electric field is just randomly oriented. This is called unpolarized light. However, there are ways, and we're going to get into a lot of them in a second, where you can force the light to all line up. And what I mean is that all the light, all the electric fields, all in parallel. And if all the electric fields are in parallel, all the magnetic fields are parallel. On this bottom, the two of just E fields, the middle one and the right one. The middle one would be unpolarized light. All the electric fields can point any direction. But the right one would be polarized light. And polarized light is just all of the electric fields are forced to line up. You know, just for fun, let's switch glasses because this is going to come up today. Going for polarization. So, when you have linearly polarized light, and there's other types of polarization, we're going to talk about linear for now. When you have linear polarized light, as I said, all the electric fields are lining up. And there's a lot of ways to do that. The main ways, though, are selective absorption, reflection, and scattering. And I want to start with selective absorption because that's the easiest. When I put these sunglasses on, I am polarizing the light that hits my eyes because these are polarized sunglasses. And how it works is selective absorption is you take a material, and I'm just going to jump ahead. The material is called a Polaroid. It was first discovered in 1932 by a man named E.H. Land. It's a sheet with long chains of hydrocarbons. But what you do is you take a polarizer and you shine light through it. And the polarizer on a selective absorption will transmit all electric field will transmit all electromagnetic waves that have an electric field parallel to a plane it decided. Now, sunglasses are polarized up down. So if you're wearing glasses normally, only light any light that passes through will be not polarized, but when it passes through your glasses will be polarized up down. The electric field will be straight up, straight down. I'll get into why that is in a little bit. anything that is not straight up, straight down will not pass through the glasses and will be absorbed instead. And that's the idea, that it will take unpolarized light that's pointing in any direction and it will make it all up-down polarized. And if you take a second polarizer, you can actually see this in action. So I got my glasses and my wife's glasses. Actually, you know what? Let's not use the glasses. Let's use this video. And so I have two polarizers, right? And when I put this in, most of the light passes through. But right now, the one in the back is only allowing light through polarized a certain way. The one in front is only allowing light through that's polarized a certain way. And if they're parallel, to each other, it'll allow basically all the light through. But if I start turning them relative to each other, it'll get darker till it allows no light through, and then brighter again when it can allow light through, and so on. And it doesn't matter which one I turn. I can make this go from allowing light to not allowing light just by changing the angles. And now I'll switch to these glasses. And I wanted something with more color, so I just grabbed a random comic book off my shelf. That if I put my glasses here, any light that passes through my glasses is going to become up-down polarized. If I put these glasses here, any light going through these glasses will become up-down polarized. And so if I put both of them inside each other, I can see through them just fine, even though the camera can't. What if I do, oh, that's too reflective. Damn.
Maybe the lens itself is polarized.
Oh, it is. Oh, yeah, there we go. This is working. So I just brought them up real high. So if I put them up here, it's allowing basically all the light through because both are up down. But if I take these glasses and I put them 90 degrees, this is only allowing things up down. But this one turn is only allowing left right. And so when I bring this up, it's not going to allow any light through. And if I start varying the angles relative to each other, I can go from not allowing light to allowing light just by changing these angles.
Isn't there a weird phenomenon when you get like 3 polarized lenses in a row?
Not really. It'll just be another one blocks it.
I thought there was like a thing where like when you get them 90 degrees from each other and then you get a third one and shine it through, it somehow like magically lets light through again. I don't know.
Not
Maybe
that I
I'm
know of.
misremembering.
I've never heard of that. I'd have to look into it, but I don't know of anything like that. And there's the general idea. If you have two polarizers, if they're parallel, it'll allow light through. If they're perpendicular to each other, they will not allow light through. And so parallel, we're all good. Perpendicular, no light. And in fact, the intensity of light that passes through two polarizers can always be given with Malice's law, which says the intensity of light through two polarizers equals the intensity that you started with times the cosine squared of the angle. Now, cosine is a maximum at 0 or 180, because the cosine of 0 is 1. The cosine of 180 is -1, but it's squared, so they're both 1. And so anytime the two polarizers are at the same angle, or, opposite angles, you have a maximum light through. Cosine is 0 at 90, though, and 270. So anytime they're at 90 degrees from each other or 270 degrees from each other, no light will pass through. And that's the general idea. Now, I'm doing all this with sunglasses. So the question is, why the hell are we bothering with sunglasses being polarized? And this is one way to polarize light, the selective absorption. But there's another more common way in nature that light gets polarized. And that is polarization by reflection. And here's the idea. Whenever light is reflected, the light will either stay non-polarized, become completely polarized, or somewhere in between. Now, for the record, the light only stays completely non-polarized at 0 degrees. So if you have light shine down and bounce straight up, it will not be polarized. However, for any other angle, light will become polarized, and light will become polarized at an angle matching the surface. So let's start with these two GIFs I have. I'm going to start with the upper one. When light hits this dirty ass pond filled with, I'm guessing, tadpoles, when the light bounces off it, it will be unpolarized from the sun. But when it bounces, it will become horizontally polarized because the surface of the lake or pond is horizontally polarized, like shown in the picture to the left of it. The glasses are done in a way that they're up-down polarized. They don't allow light through that's horizontally polarized. And so when you look through the glasses at that pond thing, suddenly you don't see the reflection. You can see into the water. And that's the reason we use polarized sunglasses. It reduces glare. Now, really, it only reduces glare off horizontal things, but most stuff that we have to deal with glare off are horizontal. This is also used for cameras. The bottom GIF is literally from an advertisement for a camera's polarizing filter. And it's showing, hey, look, you put our filter on your camera, you don't have glare in your shots. And it's just because reflected light is polarized. And by putting a polarizer in front of your camera, or in the case of sunglasses, in front of your eyes, you're going to go and make it that, oh, any light that's bouncing off something flat, like snow or an ocean or a small ass dirty pond of water, the glare will go away. And you'll be able to see through and not see the light bouncing off of it, because the light bouncing off of it will be blocked by the glasses. Any questions?
Nope.
Now, if you look at this upper GIF, this shows it better here. When the glasses are on, you can still see a little bit of reflection right in the middle. Why am I pointing? You can still see a little reflection right here from the sun. That's because when light bounces off something, it's only sometimes completely polarized. As I said, it's partially polarized normally. Most of the time when light reflects, there will be some of it will be polarized, some of it won't. Majority of it actually ends up being polarized, but how much becomes polarized depends on the angle. A man named Sir Davis Brewster worked out for what angle the light is 100% linearly polarized. And this angle is known as Brewster's angle since it was discovered by Sir Davis Brewster. And what Sir Davis Brewster found is that light will become 100% polarized when it bounces off a surface anytime the angle of reflection is the same as the angle of refraction. What I mean is if I shine light in at an angle theta p, when I shine light in at a theta p, some will reflect, some will refract, assuming it's not a mirror, assuming it's like a piece of glass or water or something. And if I say this theta 2, my refracted light, and I can say my theta O, my reflected light, and they will be polarized when theta O equals theta 2. Now here they use it as the angle between them is 90, but that's because it's off a straight line. So theta O plus theta 2 equals 90 is the same as the angle between being 90. Now what I can do with that is I can say, well, following the law of reflection and how this is labeled, anytime light reflects, the angle of incidence equals the angle of reflection. But here I call the angle of incidence theta p for Brewster's angle, which is weird that Brewster's angle is a p, not a b, but it's for polarization. And so that means if theta O equals theta 2, well, theta p is the same as theta O, so theta O plus theta 2 is 90, I should say. And if theta p equals theta O, that means theta p plus theta 2 must be 90 degrees. And we also have Snell's law, right? That n1 sine theta 1 equals n2 sine theta 2. I'm just calling n1 theta p because it's Brewster's angle. And if both of these things are true, if theta p plus theta 2 is 90, and if n1 sine theta p equals n2 sine theta 2, I can go and I'll take my Snell's law and divide both sides by theta 2, then divide both sides by n1. I'll then take that equation, and for theta 2, I'll say theta 2 equals 90 minus theta p. Now, I don't know how many of you know this off the top of your head, but I'm just going to tell you, there's a trig identity. The sine of 90 minus theta is equal to the cosine of theta. It's a trig identity. And the sine of theta divided by the cosine theta is the tangent of theta. And so Brewster's angle, the angle with the maximum amount of polarization, will happen anytime your angle is the inverse tangent of N2 over N1. Well, N1 is whatever you're in, N2 is what you're going into. So like if you want to shine light off water and look at light bouncing off water and try to get the light bouncing off water to be fully polarized, your angle has to be the index of refraction of water divided by the index of refraction of air. It's about 50 degrees. But that's the logic. Okay.
All right.
Now, one last thing we got to talk about with wave physics, which won't take too long, and then the rest of it I'm going to talk about some optical devices, because this is the last optics chapter. And that's resolution. So we're going to finish with. If you want to look at something with your eyes, through a lens, through a microscope, through a telescope, through anything, how small of objects you can distinguish, how tiny of a anything you can actually tell apart, you can resolve, is actually limited due to the wave nature of light. If you look at an object through a thin film, through a single slit, and honestly, okay, our eyes, we're going to get into eyes in a little bit, but our eyes, what they really are, is a tiny hole that light passes through. It's what the eyes are. So we're basically doing single slit diffraction anytime we look at things through the eye. And if we have an image that we're looking at, right, we can say that light's going to come from the top of the image to our eye and from the bottom of the image to the eye. But as they pass through this thin slit, each one is going to have a small interference pattern, just like a single slit. And so you'll get that a bright spot where the thing most is likely, but some kind of wavy spots after. If you look at things, and we're looking at resolving between two objects, right? So we're saying, here's object one, here's object two. We want to be able to tell those different items. And we don't want to just see a blur of just the stuff. We want to see two separate items. If the two sources are separated enough that their central maxima, when you have interference, are separate, our brain can tell them apart. This would be the same as the lower left picture, that S1 is leading to this orange diffraction pattern, and S2 is leading to this blue diffraction pattern. And the central maxima of S1 and the central maxima of S2 are not overlapping. And our brain can interpret that and separate and figure it out. But any time the two sources' central maxima overlap, they cannot be resolved. And our brain can't tell where item one starts and item two ends. And our brain just mixes them into a simple single thing. And it's not just our brain, it's any optics. A camera with fancy optics will have the same issue. And it ends up that if you look at something with camera, eyes, anything, that anytime there will be a diffraction pattern. And if the central maxima overlap, the two objects cannot be told apart and cannot be resolved separately. This can actually be mathematically solved using Rayleigh's criterion. And that's just a fancy way of saying it. When the central maxima of one image falls on the first minima of another image, they are said to be resolved. So it's basically when this maxima lines up with the second maxima. That is as close as something can be. Anytime they're closer, we can't tell them apart. If they start just overlapping, you just see some weird oval thing in between. If they overlap fully, you just see this one object and not the two separate objects it is. And this will happen. The minimal angle that things can come in at will actually end up being that the minimum angle in radiance for something to be coming through a device will be given as the wavelength of light over A, where A is the size of the slit, aka the size of the aperture. But the thing is, that's for a slit. Most of the time when we look through things, we don't use a slit. We don't have a vertical iris. We have a round iris on our eyes. And most cameras are round. They're not a thin slit. You mathematically can solve this for a round camera. And what we get is for a round camera or an eye or just a round hole instead of a slit, that equation would change as follows. And I'm not going to play that video. I'm actually blanking. If we have extra time, I'll play the video at the end, but I'm pretty sure I won't have time. And we'll say the minimal angle is going to be given as the wavelength over the diameter of the aperture.
Does this whole topic kind of relate to how during like a solar eclipse, when you look at like shadows under trees, you can see like little crescent shapes like all on the ground?
Kind of, yes. It's not quite because of the resolution. The reason that happens is because the light. Okay, this is the pinhole camera's idea, and I think this is what the video is about. Maybe I will play it. Yeah, I will play it because that gets into that.
Famous scene in The Lord of the Rings where the elf Legolas claims to be able to count the exact number of horsemen 5 leagues away, and on top of that, he can tell their leader is very tall. But even with the most perfect eyes possible, would anyone be able to see that far? When we see, we're looking at light that's traveled outwards from a light source, bounced off an object, passed through the lens of the eye, and been focused into an image on the retina. Except light isn't a particle traveling in perfectly straight lines. It's a wave, and therein lies the problem, both for us and for Legolas, because any wave, whether water, sound, or light, traveling through a small opening will become spread out by a process known as diffraction, which for light essentially blurs the image. You can see this with a telephoto camera lens where the camera aperture has been made very, very small. Small details in the photograph start to become spread out and even indistinguishable. Or if you hold the edge of a piece of paper in front of your eye and try to read past it, small words will become blurry. The blur that a small point of light spreads out to become is called an airy disk, and the size of the airy disk for distant tiny objects depends only on the wavelength of the light in question and the size of the opening you're looking through. So for visible sunlight and a human-sized pupil, diffraction limits us to at best be able to distinguish objects that are bigger than 7/1000ths of a degree. For example, an object 1 centimeter in size, 100 meters away. Another way of putting this is that everything 100 meters away and smaller than 1 centimeter gets blurred so it appears to be about a centimeter in size, no matter how small it really is. Subtle details smaller than 1 centimeter blur away. So when Legolas, who has very human-sized pupils, looked at the riders of Rohan 24 kilometers away, diffraction tells us that everything smaller than 3 meters would have been blurred to about 3 meters in size. Perhaps he could still count the number of horsemen, but he definitely couldn't distinguish their heights to within a few centimeters. Unless Legolas could see in ultraviolet. Shorter wavelength light diffracts less, so if he could see in the extreme UV, then he'd be able to distinguish objects 10 centimeters in size, almost enough to discern the height of a man. Except that pretty much any kind of air absorbs extreme UV light, so even if he could see UV, Legolas would have been left in the dark. Or maybe it's just magic.
Yeah, that wasn't actually the video I thought it was. So that didn't answer your question. Sorry, wrong video. So that was about this one. Your question was, I'm going back because now I got separated. What was your question again?
It was regarding solar eclipse and like
yes,
the
okay. So yeah, I thought that was in that video, but that's a different one. So the reason for that, it gets into the pinhole camera idea, and there might be a video later on in the class, but I'll go through it anyways. What it is the process of putting light through a thin hole kind of focuses onto a point. And I'll talk about this a little bit when I get into how we see and things. But if you shine light on anything, like say I have an image and we look at it or put light through a small hole, light will come from all angles. And if light passes through, it's going to have to, make it through. Light will also go this way, this way, this way, this way, but only light coming at certain angles will make it through the slit, forming an image. And so the reason you see the eclipse is because the object you see has that shape. When it passes through a small hole, we see that shape passing through. It's just the way imaging works.
Okay.
I thought that was that video. I think that's a different video that I probably won't get to today. So, dealing with the Rayleigh criterion, let's do a problem. The Hubble Space Telescope has a diameter of its aperture of 2.4 meters. What is the limiting angle of resolution at a wavelength of 600 nanometers? And what's the smallest crater it can resolve on the moon? I don't know why I did the moon's distance from Earth, because that's not where the telescope is, but we'll run with it. So, there's the equation. If you want to find the smallest angle it could go through, it's just going to be the wavelength over the distance of the diameter. And that'll be the angle in radians. Now, if this wanted to go and look at something 3.84 times 10 to the 8th meters away, that angle, that when we say something's far away, what we're going to say is that distance away, that would be the radius. And the size of something would be the arc length. For anything, the arc length is the angle in radians times the radius. And so the smallest thing we can resolve will just be the angle in radians times how far away it is. And that'll tell me I can see something as small as 117 meters across. And that's it. Anything smaller than 117 meters, we can't resolve.
Huh. All right.
Otherwise, that is the diffraction. So that is diffraction. And that's everything I'm going to do about diffraction. But I have 20 minutes left. And so I want to spend the 20 minutes talking about other optical effects from diffraction, but also reflection, refraction, and all the other things we talked about. But is there any question about diffraction before I do that?
Nope.
Okay, let's talk about optical instruments, aka other things that cause this to happen. And the first optical instrument we're going to talk about is the eye. It's how we see, it's important. This is how your eye works. You have a cornea that's in the front. Light passes through this structure. It then goes into the aqueous humor, which is some liquid behind it, and then goes to your pupil. Your pupil, when it's dark, your eyes open up. When it's bright, your eyes close, or from other stuff. All that is a variable aperture. That's an aperture that can open or close to allow more light or less light. But then the light hits a lens that is literally the same as a lens like the lenses we've been talking about, or like my glasses. And all the light can be shined into the back of your eye on the retina. What it is the lens in your eye is just a converging lens and uses the same logic as a converging lens. It'll take any light that hits your eye and focus it to a point. Now, the interesting thing is that the muscles around your eye can go and bend the lens and take the lens and warp it a little bit, making it fatter in the middle or maybe thinner in the middle. And the muscles in your eye, when it does that, can change the focal length. Of note, if an object is infinitely far away and you try to look at it, aka you stare off in the distance, your focal length is about 1.7 meters. Or 1.7 centimeters, sorry. But your eye will flux to move that focal length, and it can change it pretty heavily. Now, for everyone, there is a near point and the far point. The near point is the closest distance which the lens in your eye can focus light. This changes as you age and can go from 15 centimeters to 500 centimeters. That's why most old people start needing reading glasses. That's because as they age, their eye stops being able to make such a small focal length. And if your focal length is like 18 centimeters, that means you can put something 18 centimeters from your face and focus it. And any closer, it gets blurry. But as I said, it can get all the way up to 5 meters at an older age. The fall point is the furthest something can be, and that you can still focus it. And normal vision, the fall point is actually infinity. The only reason you can't see something super fall is because of the Rayleigh criterion that you just stop being able to resolve it. but you still theoretically should be able to focus it if it wasn't for the fact of the size of your aperture of your eye. Now, we all know that isn't good for everyone. People can become far-sighted where they can't see something far, or nearsighted where they can't see something near. I personally am, sorry, that was backwards. Far-sighted where they can see things far but not near. I said that backwards. And nearsighted where they can see things near but can't see things far. Personally, I am nearsighted. I can read just fine without my glasses, and I do all the time. And this screen, I can kind of read without my glasses. But if I look out the window, I see a blur of splotch for the outside world. The reason for this is when someone needs glasses is literally their eye's lens, the focal length, is messed up. On a person with perfect vision, the lens of their eye will focus light right on the very back of their eye. But for a far-sighted person, it'll accidentally focus the light too far back and will focus the light behind where it should. And you need a converging lens to correct the light to make it focus on the correct spot. For a nearsighted person, it focuses the light too early. And you need a diverging lens to make it so light is focused in the right spot. And so what is your nearsighted or farsighted? It's just the lens that makes up your eye. Its focal length isn't what it should be. And it doesn't focus light to the right spot. Now, optometrists, aka eye doctors, what they do is they then make lenses with a set focal length in an effort to make the eye focus in that spot. But if you ever get glasses, or I don't know how many of you have glasses, but whatever, they always they don't talk about the focal length of the lens of your glasses. If you actually get the terms, they talk about dioptose. A diopter, which is just using the symbol capital P, is just the inverse of a focal length, 1 over the focal length. And this is more commonly used because if you look at all the lens equations, 1 over Q plus 1 over P equals 1 over F. It always depends on 1 over F, not F. And so they just go straight to that. And yeah, we can use this. And what it is
sorry, I was just going to ask, is this where like the plus 2.5 or minus 1.25
that is
comes
exactly
from?
where I'm going with this. Yep.
All right.
Because what it is theoretically something at your fall point, an object at the fall point, should be focused on the back of your eye. That's what we were started with, right? That the fall point should be focused. What they do is they figure out what your fall point is and how far off it is. And when you talk about the dioptose, if it's like negative 0.2, and this was the other video that I was thinking that I'm not going to play because time reasons, but negative 0.2 or positive 0.5 or so on, that's just saying how far off you need to change that focal length, or the inverse of the focal length, near or far. Okay. Now we can correct our vision a lot of ways. That's just glasses. Well, I did eyes, then glasses. But if something's really small, we want to might want a simple magnifying glass or a simple magnifier. If you're looking at something with a magnifying glass, let's assume you're looking at something a distance away, P, right? The size of the image will depend on the angle from the eye, right? Because we can basically say the height of the image would depend on this theta. When you move closer to an object, it looks bigger as theta gets bigger. And we can do that with all the lens equations we covered. 1 over Q plus 1 over P equals 1 over F. The idea of a magnifying glass is you are placing a converging lens in front of the object inside the focal length. When you do that, as we covered last chapter, you get an enlarged upright image. Now, for magnification, when on a magnifying glass, they usually don't talk about the same magnification we've been doing. They normally talk about the angular magnification, where the angular magnification is the angle over the initial angle. And it's just Yeah, what angle the virtual image makes versus what angle the object makes. And for most people, the near point of their eyes is about 25 centimeters. So we're going to have to make sure we're within that range. Now, you note magnifying glasses, you have to have them near your eye. That's because they have to be within the focal length. And if they're going to have to be within the focal length, that means that the image is going to end up, that means the image is going to have to probably be near your near point, which is usually for most people at about 25 centimeters, but it's a virtual image, so it's going to be behind. Using our simple 1 over p plus 1 over q is 1 over f, and assuming that the image is at the near point, 25 centimeters back, if we rearrange a little bit, you can get this equation. And this says where you want something to be to see it at its largest, assuming f is in centimeters in this case because the 25 was in centimeters. If I wanted to work in meters, I'd have to make this 0.25 instead. And using these sets of equations and a whole bunch of crazy math that I'm not going to worry about too much, but another small angle approximation, and kind of the same logic I did before, I can find that the max size something gets, which once again is going to be when h prime is at the fall point, 25 centimeters for most people, and doing some crazy math. You can find that the magnification angular for most people, putting a magnifying glass in the best spot, will just be 1 plus 25 centimeters over the focal length of the magnifying glass. And that only can get a magnification so far, that you can make something bigger with a magnifying glass, but only so much. And to make something actually bigger, you're going to need to do crazier stuff. And this is what gets into the microscope. A compound microscope. We're not doing electron microscope. That's something else. We'll be doing this to the nth degree. What you do with a compound microscope is instead of one lens, we use two. Both lenses separated by a distance L. And what you're going to get is a very much enlarged image, a virtual one, an inverted one, but one that's much bigger. And the reason why is you put the lens near the thing with a very short focal length, and then an eyepiece of a little bit larger of a focal length, and separate them from a distance L. And the lateral magnification, not angular magnification now, but the regular magnification like we did last chapter, which we always know is negative q over p, will actually normally go by the distance between the things over the focal length of the eyepiece. Or the angular magnification we can follow with the same logic. Oh, sorry, this is of the objective piece, this is of the eyepiece. Sorry, I did them separately. And the overall magnification is actually just going to be the two multiplied together. And so a compound microscope can magnify greater, because it would be the same as a magnifying glass plus a second piece magnifying separately. And we can get things many, many times bigger. Now, this logic can also be used to look at things very far away in a way we can see. That the logic of a microscope with this magnification is actually the same as the logic of a telescope. Most telescopes come in two flavors, refracting or reflecting. And I have both of them here, good. But it's the same idea. It is using multiple lenses, or a lens and a mirror in the case of refracting, in order to bend the light and make an image bigger. A refracting telescope is exactly the same as the microscope. It's just we're switching which way has a larger focal length. You're basically looking through a microscope backwards. And you'll see an image that's going to look much bigger than it would look normally, inverted. Now, normally we talk about the distances FO plus FE. That's the distance from one lens to the other. And when you want to do this correctly, it'll be the focal length of the objective piece plus the focal length of the eyepiece. If you separate the two lenses by that much, that'll maximize how big something will look. And we can do the magnification of the same logic. However, lenses distort light near the ends, and that when you look through lenses, everything at the very edges is usually pretty blurry. Just think about when you look around. Well, that the very edge of your vision, the periphery of your vision, is normally a little blurry. You can't see well. That's just because your eye is a lens. And the same idea when you look through any other lens, that the edges of the lenses, is this going to work? Hey, that's going to work. We're going through a lens. That my head in the middle is fine. But when I get near the edges, I start getting distorted. And that'll happen anytime you refract, especially through multiple things. For this reason, we often use a reflecting telescope, where the light goes and hits a curved mirror, bounces off the curved mirror to get a directing mirror and into an eyepiece. This will create a more powerful telescope that can make things much, much bigger using the magnification of the concave mirror and then an eyepiece. Because it goes through fewer lenses, you have less error. The reason they get blurry at the end of a lens is light lost in the lens. But if light is refracted, you don't lose as much. This is a much more powerful microscope or telescope, but they're much harder to make because you need a really, 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 really big, well-polished, perfectly shaped mirror. The largest ones in the world, or the largest one in the world is in Hawaii, the diameter of that mirror is 10 meters. The largest single mirror one in the US, because that one's kind of a bunch of mirrors put together, has a 5-meter diameter. Refracting telescopes, largest one only has a 1-meter diameter, but is not as good for resolving things.
I don't know if he still does, but my cousin actually worked at the one at Hawaii.
Oh, that's cool. That is actually very cool. Yeah, it can. That one's a powerful one, and it's off kind of more towards middle of nowhere Hawaii purposely to have less light pollution.
Yeah.
But that's the kind of the wrap up of optics. That's at this point. That is the end of classical physics. That is all the physics we can describe. Yeah, using classical physics. Everything we're going to do here moving forward is what is called modern physics. Modern physics being 1920s. We did a little bit of modern physics mixed in here, most of this, but not much. And now we're going to get into some of the crazy things of why is light a particle and a wave, and what does that mean? And get into, we're just going to get into some crazy shit. Let's just say it like that. But I will stop there. We will do practice problems on Friday. The problems will come up in 2 minutes. So if you want to look at them ahead, you probably should. But other than that, have a good day.